Hi everyone. This video is going to be about the Platonic solids, which we call the convex regular polyhedra, and it's also going to be a little bit of a discussion about the semi-regular polyhedra. But to start off, I'm just going to be talking about these 5 solids here. So each of these are what we call regular polyhedra. This first one here, the reason it's a regular polyhedra is because it's made up of all regular polygons. Right, so if I just kind of take a tour around this piece here, we've got all equilateral triangles on here. One way to analyze these is to look at what's happening at each of the vertices on here. So at this vertex, you can see, for example, this one here, we've got 1, 2, 3 equilateral triangles meeting at each vertex. And I've kind of demonstrated that over here with this net here, if I flatten that out. With tiling, we saw, so this was 2-dimensional tiling. With tiling, we saw that at each vertex we needed to have 360 degrees, but since we have a third dimension now, we can actually have less than that. We can have less than 360 degrees occurring at each vertex, which is what we've got going on here. So these 3 triangles are each contributing 60 degrees, 60 degrees, 60 degrees. And then what's left over is this angle here. And this angle, you can kind of think of this as being the gap, right, that we need to fill in. So that gap in this case is 180 degrees, and this is one way to think about the measure of this object's spherical deviation. So a spherical deviation is what we looked at last time. So spherical deviation, I'm going to use that delta to describe this. But for this tetrahedron, that's going to be 360 degrees, and then we subtract all of these angles that are happening at that vertex. So minus 60, minus 60, minus 60. And then what we're left with is that gap there. Just to show you what's happening with this particular net and how these 3 triangles form this tetrahedron, I'm just going to quickly, so this is going to get misaligned here for a second, but I'm just going to quickly rotate these pieces. Like that, so you can kind of take these missing pieces and fold them a little bit. So I'm sort of folding these pieces up. Sorry, it's a little unwieldy here. But if I take those pieces and fold them up, you can see that I'm kind of taking care of that gap that I've got there by closing that gap there. So I'm sort of folding these 2 pieces, and that forms something that looks a little bit like our tetrahedron here. So I'm going to start writing down these spherical deviations next to these ones, and we can do the next. I'm going to do the spherical deviation for all of these, but I'm going to start doing it a little quicker here. Okay, so we've got spherical deviation here for this one. we've got delta is going to be equal to 180 degrees. That's our spherical deviation. And this one's called a tetrahedron. This one here is made up. If we look at what's happening at each vertex, we've got 1, 2, 3, 4 equilateral triangles this time around. So 1, 2, 3, 4. And that's represented here as well. In the net, we've got 1, 2, 3, 4. And so our gap here, right, this gap, that's less than 360 here. We've got our spherical deviation this time is going to be equal to 360 minus, and then we've got 1, 2, 3, 4 triangles. So each of those are contributing 60 degrees. So this time around we get 120 degrees. Okay, so our spherical deviation is going to be 120 degrees. And then we can say that this is an octahedron. Right. So something worth pointing out at this point is if you look at this octahedron, at each point on this octahedron, we've got the same situation going on. So if you look at any vertex in this octahedron, we're always going to have 1, 2, 3, 4 triangles, and they're always going to meet at that exact same angle setup there. Right? So just something to keep in mind that all these vertices are going to be the same. Very similar situation with this next shape, which is the icosahedron. So the icosahedron, now if we look at each individual vertex, we've got 1, 2, 3, 4, 5 equilateral triangles, meeting at that point there. So we can say that our spherical deviation this time is 360 minus 5 times 60, right? So that this gap here, right, our spherical deviation, right, that part that's missing there, is just going to be 60 degrees. We're going with this tetrahedron, octahedron, icosahedron. You'll notice that the spherical deviation is going down here, and if we compare these three shapes, we can say that I think that out of these three shapes that we've looked at so far, this one definitely looks the most like a sphere, right? So that phrase spherical deviation, this will be something that your quiz is going to ask you. That spherical deviation is sort of how much does this shape deviate from a sphere, right? So this measurement, 180, says yes, that's very high. This is very different from a sphere. It deviates from a sphere. But this relatively low one, 60 degrees, says that we're deviating a little less here. Okay. So that's the first three shapes that look like that. This next one, very familiar. This is just the cube. It has other names, but I'm just going to call this a cube for this class. So we've got a cube, and just like the other Platonic solids, we're going to look at what's happening at each of the vertices. So at each vertex, I'm seeing 1, 2, 3 squares meeting at that point. So if I were to draw that same sort of net on there, I've got 1, 2, 3 squares, and then this gap. There, so that gap, right? Just like the other one, we can say that spherical deviation this time is going to be 360 degrees minus 90, 90, 90. So we can put our spherical deviation for this one is going to be equal to 360 minus 270, which is 90 degrees, right? That's our gap in between there. So a little less like a sphere than this one, but a little more like a sphere than our octahedron. Okay, this last one is actually going to have the lowest spherical deviation of all of them, because if we look at 3 pentagons put together, these are 3 regular pentagons. So if I take these 3 regular pentagons together, right, because that's happening at each vertex, we've got 1, 2, 3 regular pentagons happening. This gap is actually pretty small here. So that gap, which is our spherical deviation, is going to be 360 minus, well, maybe you know what this angle is off the top of your head, maybe you don't, but this would be a good one to memorize. We can certainly figure it out by using this formula, right, where n is equal to 5. That'll tell us that this is 108 degrees each time. So we've got 108 minus 108 minus 108. So we can say that delta for this one is 36, and that's going to be the lowest spherical deviation out of all these shapes here. Okay, so we can measure the spherical deviation, and apart from telling us how much or how little something looks like a sphere, this is actually really useful in one of the formulas that we're going to use here. So I'll just go ahead and let you know what this last shape is called. This is going to be our dodecahedron. Dodecahedron. Okay. All right. So we know how to find the spherical deviation, and what do we do with that? Well, spherical deviation is really useful because we can use it to figure out the number of vertices pretty easily because of a really nice formula that we've got called Descartes Formula. So I'm gonna just start doing some notes here. So we've got Descartes Formula. Just write it this way. So we've got Descartes Formula. So Descartes' formula says the sum of the spherical deviation at all vertices of a polyhedron. Is equal to 720 degrees. Really nice, useful formula. If we know the spherical deviation delta at a particular vertex, which is what we just found here, we can take advantage of the fact that all these vertices are going to be the same, right? The spherical deviation at every vertex is going to be the same. So we can say that delta times however many vertices there are, right? That's going to be the sum of the spherical deviation at all the vertices, and we can say that's equal to 720 degrees. right? So really nice. You can see if we can figure out the spherical deviation, we can figure out the number of vertices very easily. Just a small bit here. So let's try and do that with this shape here with the icosahedron. So for the example, we can say how many vertices are in an icosahedron. Right, how many vertices are in an icosahedron? And let's say we know that at one vertex, we know that at one vertex, the spherical deviation is going to be equal to, so we decided this was 360 degrees minus 5 of those triangles. So we know that delta is going to be equal to, sorry, not 36, 60 for the icosahedron. So we can just plug that into Descartes' formula. So it says, so 60 times the number of vertices is equal to 720. So V is going to be equal to 12 in this case. So among this icosahedron, there are going to be 12 vertices on there. We didn't have to count them individually, right? Which is a really nice feature of this, right? For something like a cube or either these two, pretty easy to count the number of vertices, but this is just nice for something like this or something like this. Okay. So this I would consider the one of the 3 formulas that we're going to be using a lot in this chapter. So I'll go ahead and write them out, those 3 formulas that we can use, and then we'll try to answer some other questions about them. So we've got our first formula is going to be that the sum of vertex valences is going to be equal to the sum of the face valences. And that in turn is going to be equal to 2 times the number of edges. All right. You probably recognize this one, right? This formula is exactly like it is for maps, right? So we looked at, again, right, maps where we had, for example, the valence that looks something like, we could look at this vertex and say this has a vertex of 1, 2, 3. Right. For polyhedra, we actually have this nice, so for these 3D shapes we're looking at, we actually have this nice property that, remember, all these vertices are going to have the same vertex valence, all these faces are all going to have the same face valence. So just as a reminder, we've got vertex valence is going to be the number of edges that connect to each vertex, and then the face valence, so this would have a valence of 3, and then the face valence is how many edges make up its boundary, so we could say 1, 2, 3 for this one. Okay, so that's the first formula that we use a lot. The second one is also carryover from what we saw in chapter 5, where we said the number of faces plus the number of vertices minus the number of edges is going to be equal to 2. And that's exactly how it operates with maps, so we should be familiar with this one. And then the last one is what we just saw, Descartes' formula. So that says that spherical deviation at one individual vertex times the number of vertices always adds up to 720 degrees. Okay. So, a lot of the questions, almost every question that is not just a kind of what's going to happen at this shape sort of thing, is going to be dealing with these 3 formulas. So I can ask a question, for example, that says how many edges a dodecahedron. So how many edges make up a dodecahedron? Great question. Right. How many edges make up a dodecahedron? I'll go ahead and just create one here so we can look at it. But just be aware that they may give you this dodecahedron to look at. Ooh, that's not a good looking one. Let me just copy the one that I have. So again, they may give you a dodecahedron to look at, they may not. So you want to be prepared to kind of tell me what a dodecahedron looks like without having one available necessarily. Okay. So here's our dodecahedron. I'll maybe rotate it to a little more pleasing angle. Okay. So how many edges make up a dodecahedron? Well, one thing we know is the spherical deviation, right? And if we try to plug directly into this formula here, we don't know the number of faces necessarily. We don't know the number of vertices or the number of edges yet, so we can say that we know that the spherical deviation is going to be equal to 36 from a previous problem. So we know delta is equal to 36 from formula 3. We can say that delta times V is equal to 720. So we can definitely figure out the number of vertices, right? That's one step. So the number of vertices was pretty easy to figure out. That was going to be 20 in this case. Right. So we've got 20 vertices. We can try plugging it into this piece here. But we still need to know the number of faces. And while I can pretty easily do this, or maybe you can use the, I forget if this is I believe this is the Greek root for this, dodeca, right? Saying that that's got 12 faces there. Let's see if we can figure that out using this top formula here. So this vertex valence here, this vertex valence here Again, we're talking about three regular pentagons that are meeting at each vertex, okay, with that little gap in between there. So, so we can say at each vertex, we have three pentagons. So I'm going to put that on a new line here. We have three pentagons meeting. So let's think about what is the vertex valence. So the vertex valence is how many edges are going to be meeting at this point here. And I look at this and I say, well, each vertex is going to have 1, 2, 3 edges. So we'll say each vertex valence is going to be equal to 3. And then we can also maybe talk about each face valence. So each face valence here, remember, this is, for example, one face, this red one here, this is one face of our polyhedra, and that's going to be made up of 1, 2, 3, 4, 5 edges. 1, 2, 3, 4, 5 edges. So you can abstract this and say, if you can tell me what's happening at each vertex, right? We've got 3 pentagons. This 3 here tells you what your vertex valence is. The fact that this is a pentagon at each of these faces tells me what your face valence is. Right? So, anyway, looking at the formula that we've got up here, this says the sum of the vertex valences is equal to the sum of the face valences is equal to 2 times the number of edges. Let's look at just the vertex valence for now. We could always figure out the number of faces later, but if each vertex has a valence of 3, then all 20 of these, right, since they're all identical, each of these 20 vertices has a valence of 3. We can say that the sum of the vertex valences we know that that's equal to 2 times the number of edges. And that sum of the vertex valences is going to be right, each individual vertex valence times the number of vertices. Right, so I'm just kind of breaking down that sum of the vertex valence. Each vertex valence we know is 3. Number of vertices here we figured out was 20. So we can say that 60 is equal to 2e, and that tells us that the number of edges is going to be 30, right? Which is what we were trying to figure out originally. If you were asked for the number of faces, again, we could figure that out by using that second formula there. So we've got 20 plus some number minus 30 is going to be equal to 2. That ends up being 12 for the faces. Okay, so again, these 3 formulas, right? That'll be you need very little information to figure out the number of vertices, and then you just want to think about what's happening at each of those vertices, or what's happening at each of those faces. Okay. One last thing I want to show is something called semiregular polyhedra. So semiregular polyhedra, it sort of takes a page out of the semiregular tiling type of look here, where we've got, if we remember what semiregular tiling looked like in 2 dimensions, this, for example, was a regular tiling. Made out of just one shape, and then semi-regular tiling. I think the example that we looked at the most was these octagons, and then we had squares in between them. Okay. Right. So this semi-regular tiling used 2 or more different regular polygons. So all of these are just using one shape to define them, but what I want to show you is some semi-regular polyhedra. So one way that we can make semi-regular polyhedra is to take something, and I'll work with this cube first, and we'll use this technique called truncating. Right. So truncating a cube involves taking, each of these vertices and sort of applying some sandpaper to it. So you can picture kind of taking an angle grinder, some sandpaper, and just kind of sanding down each of these vertices. And I'll show you what that looks like. So they call it truncating. I think of it in my 3D work. I think of this as beveling. That's the same thing. So if I go ahead and just take a little bit of sandpaper to each of these vertices and apply that truncating, then I get a shape that looks like this. I'll go ahead and show that. Actually, let me get another material. Sorry about that. Okay. So if I bevel those vertices, sorry, I just want to make sure that those bevels have that same color there. Okay. All right. So all that truncating did was, now I've got, instead of a cube, I've got some octagons, and then I've got some triangles here. Right. And you can kind of predict what's going to happen. What shapes are going to form on here, just based on looking at the fact that we've got 1, 2, 3 shapes meeting here, right? So that 1, 2, 3 shapes, again, that's going to create a triangle at each of those vertices. So one way to think about this is that each vertex is turning into a triangle, right? The most common kind of truncating that you'll see is something where it says I'm truncating 1/3 of the length. So if you look at this top edge here, right, let's say it's got a length of 1, then as we truncate it, we're going to truncate it to 1/3 of that original. So 1/3 of it gets truncated, 1/3 stays, 1/3 gets truncated. That's what they mean when they say 1/3 truncation. A good question to ask, if I were designing a question for this, would be to ask, once I've made this shape, all right, how many vertices are in this shape? And we can try to go through the whole spherical deviation process and try to look at some other things. But I think a good way to approach these kinds of problems with these semi-regular polyhedra is to start off by just counting how many vertices do we have to start off with. So this is pretty easy for the cube. We can just count 1, 2, 3, 4, 5, 6, 7, 8. And those 8 vertices, right? If we think about if we think about what's happening when we bevel it, each of those vertices is turning into a triangle. So what was originally 8 vertices is now going to be 8 times 3 vertices, right? Because each of those 8 vertices is now 1, 2, 3 vertices. Okay, so we could say the total number of vertices in this piece here is going to be 8, the original number of vertices, times 3, this new shape. So if we look at something like this, we've got 1, 2, 3, 4, 5 triangles meeting at each point here. So we could think about, well, what's going to happen when we truncate the vertices here. Here with the cube, we got triangles, but maybe you can predict that here we're going to get something different, right? So when we bevel those vertices, we're going to get pentagons. All right, so as we kind of sand down those edges, we're going to get pentagons, and this shape should look familiar to you, right? This is how patching for a soccer ball is formed. But looking at this again, right, we've got 5 shapes meeting at this point here. So all those triangles are going to turn into hexagons. So maybe you can start to think about what patterns emerging here, right? Squares turn into octagons, triangles turn into hexagons, right? And then our beveling, of course, this shape is going to depend on how many faces are meeting at that point there. So if we wanted to talk about the number of vertices, this one, definitely not worth your time to count them, but we know from the last time that this has, let's see, I kind of forget how many vertices in the icosahedra, and we figured out that it was 12. So for this one, it was 12 originally, but now we've got not 12, but each of those 12 vertices is turning into 5 vertices for that pentagon. So the new number of vertices is going to be 12 times 5, which is 60. Okay. There is one other way that you can make semi-regular polyhedra. So I'll go ahead and just for fun, I'll show you what each of these truncated looks like. All right, so this becomes actually a 10-sided piece there. Very interesting, right? So we get that 10-sided piece there. So when we get hexagons and squares. And here we get hexagons and triangles. Right? So we've got all these semi-regular polyhedra that all just come about from truncating those spheres. Okay. So I mentioned there was another way to make semi-regular polyhedra, and we can actually get two types out of this. So one of them is called a prism, the other one's called a anti-prism, but I'll start off by just adding a, let's go with a 9-sided. All right, so we've got some 9-sided object here. And if I take that and instead of trying to truncate it, if I just do what's called an extrusion, right, I can just take that same shape and copy it above here. And if I set it to the right height here, right, if I set it to the right height here, then I just get this, which is definitely a regular polygon. All right, so I've got a regular polygon. And then at the right height, these are all going to be squares, right? So this is what we would call something a 9-gon. So it's got 9 sides on here, and then this is called a prism. Something that's similar to a prism, but uses triangles to make up this piece in between here, is something called a 9-gon antiprism. So that 9-gon antiprism, if I look at this one, so the technique here is, I think about this as just being a rotation. All right, so we kind of take this top piece here and we're just rotating it to get to the halfway point so that this vertex lines up with the midpoint of this line here. And then from here, we can just, so I won't do it all the way around here, but just enough to get the point of this. We can take each of these squares that we kind of turned into parallelograms and make them into equilateral triangles. This one here is made up of 1, 2, 3, 4, 5, 6, 7, 8, 9 squares. This one here will end up with not 9 but 18 triangles, right? Double that amount around there. Okay, that's all I've got, so I will see you soon.